Right now, as you're watching this, the Milky Way's invisible tentacles are pulling on entire galaxies, warping space, and firing jets of matter across cosmic voids so vast that light itself takes millions of years to cross them. We used to think our galaxy ended where the stars faded out. We were completely wrong. What we've discovered will shatter everything you thought you knew about our place in the cosmos. When you see the real numbers, you'll understand why astronomers are calling this one of the most mind-blowing revelations in modern astronomy. If you're fascinated by the true scale of our cosmic neighborhood and want to explore the latest discoveries about our galaxy, make sure to subscribe to this channel and hit the thumbs up. And if you could travel at light speed, where in the galaxy would you go? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. To understand how far our galaxy reaches, we first need to grasp what we mean by our galaxy. The Milky Way isn't just a collection of stars, it's a complex dynamic system with multiple components, each extending to different distances. What most people think of as the galaxy, that beautiful spiral disk we see in photographs, is just the beginning of the story. Let's start with what we can see. The stellar disk. This is home to most of the Milky Way's 200 to 400 billion stars, including our Sun. The disk spans about 100,000 light-years in diameter, though recent discoveries suggest it might be even larger. To put this in perspective, if you could travel at the speed of light, it would take you 100,000 years just to cross from one edge of the stellar disk to the other. But this visible disk is like looking at an iceberg and thinking, that's all there is. The real extent of our galaxy lies hidden beneath the cosmic surface. The Gaia Space Telescope, launched by the European Space Agency in 2013, has revolutionized our understanding of the galaxy's structure. By precisely measuring the positions and motions of over 1 billion stars, Gaia has revealed that our galaxy's disk isn't flat like a pancake, but warped and twisted, especially at its outer edges. This warp extends the disk's influence even further than we previously thought, with some stars orbiting at distances of up to 150,000 light-years from the galactic center. But stars are just the beginning. Surrounding the disk is the galactic halo, a roughly spherical region that dwarfs the disk in size. The halo contains ancient stars, globular clusters, and vast amounts of dark matter. Recent observations have traced stars in the halo out to distances of 300,000 light-years from the galactic center. These distant stars are like cosmic lighthouses marking the edges of our galaxy's visible matter. The story gets even more incredible when we consider dark matter. This mysterious substance, which doesn't emit, absorb, or reflect light, makes up about 85% of our galaxy's total mass. While we can't see dark matter directly, we can observe its gravitational effects on visible matter. The dark matter halo extends far beyond the visible stars, possibly reaching out to 600,000 light-years or more from the galactic center. Think about that for a moment. The dark matter halo is 6 times wider than the visible disk. It's as if our galaxy is wearing an invisible cloak that extends far beyond its glowing body. This dark matter isn't just empty space, it's a crucial component that holds our galaxy together, preventing the stars from flying apart as they orbit the galactic center. Recent studies using the Hubble Space Telescope and ground-based observatories have detected our galaxy's influence at even greater distances. By studying the motions of satellite galaxies like the Large and Small Magellanic Clouds, astronomers have found that the Milky Way's gravitational pull extends to at least 1 million light-years. Within this region, smaller galaxies are bound to the Milky Way, orbiting our galaxy like moons around a planet. But gravity isn't the only way our galaxy reaches into space. The Milky Way also has a magnetic field that extends far beyond the visible stars. This galactic magnetic field has been mapped using radio telescopes that detect polarized light from distant sources. The field extends both within the disk and high above and below it, creating a magnetic bubble around our galaxy that influences cosmic rays and charged particles across vast distances. One of the most exciting recent discoveries is the Milky Way's circumgalactic medium, a vast atmosphere of hot gas surrounding our galaxy. This gas, heated to millions of degrees, was first detected through its absorption of X-rays from distant quasars. Studies using the Chandra X-ray Observatory and XMM Newton have shown that this gaseous halo extends at least 300,000 light-years from the galactic center, and possibly much farther. This circumgalactic medium isn't just empty hot gas. It contains as much mass as all the stars in our galaxy combined. It's like discovering that our galaxy has been hiding half its normal matter in an invisible atmosphere. This gas is constantly cycling, with cool gas falling into the galaxy to fuel new star formation, while hot gas expelled by supernovae rises back into the halo. It's a cosmic breathing process that has been going on for billions of years. The fascinating thing about our galaxy's true extent is that it makes the dream of intergalactic travel seem almost impossibly distant. Even reaching the edge of our own galaxy's influence would require technology far beyond our current capabilities. If you're curious about why humanity might be forever bound to our cosmic island, check out my video called "This is Why We Will Never Leave the Milky Way." It explores the mind-boggling challenges of escaping our galaxy's gravitational embrace. The link is in the description and on the card above. Now let's talk about one of the most remarkable discoveries of the past decade, the Fermi bubbles. In 2010, NASA's Fermi Gamma Ray Space Telescope revealed two enormous bubbles of hot gas extending above and below the galactic center. These structures stretch 25,000 light-years in each direction. That's half the radius of the entire stellar disk. The bubbles are glowing in gamma rays, the highest energy form of light, suggesting they were created by a massive explosion or outburst from our galaxy's central black hole millions of years ago. But the Fermi bubbles were just the beginning. In 2020, the Aerosita X-ray telescope discovered even larger structures, the Aerosita bubbles, extending about 50,000 light-years above and below the galactic plane. These X-ray emitting bubbles completely encompass the Fermi bubbles, suggesting our galaxy has experienced multiple massive outbursts over its history. These bubbles show us that our galaxy's influence extends vertically as well as horizontally, creating a three-dimensional sphere of activity. The concept of our galaxy's edge becomes even more complex when we consider its gravitational influence. Every massive object warps the fabric of space-time around it, and the Milky Way is no exception. This gravitational field theoretically extends infinitely, growing weaker with distance but never truly reaching zero. However, there's a practical boundary called the Hill sphere, or Roche lobe, beyond which the gravitational influence of neighboring galaxies becomes stronger than our own. For the Milky Way, this gravitational boundary extends to about 1 to 2 million light-years, depending on the direction. In the direction of the Andromeda Galaxy, our nearest large galactic neighbor, the boundary is closer, about 1 million light-years. In other directions, where there are no massive galaxies nearby, our gravitational dominance extends farther. This creates an irregular, lumpy boundary that changes depending on where you look. Recent observations have revealed streams of stars extending far beyond the main body of our galaxy. These stellar streams are the remnants of smaller galaxies and star clusters that have been torn apart by the Milky Way's gravity. The Sagittarius stream, discovered in 1994, wraps around our entire galaxy multiple times, with parts of it extending more than 300,000 light-years from the galactic center. It's like a cosmic ribbon marking the path of a dwarf galaxy that our Milky Way is slowly devouring. The Magellanic Stream presents another fascinating example of our galaxy's extended reach. This ribbon of gas stretches more than halfway across Earth's sky, trailing behind the large and small Magellanic Clouds as they orbit our galaxy. The stream extends for more than 600,000 light-years, pulled from these satellite galaxies by the Milky Way's gravitational tides. It's direct evidence of our galaxy's ability to influence and reshape its neighbors across vast distances. But perhaps the most mind-blowing aspect of our galaxy's reach is something called the local group. The Milky Way isn't alone, it's part of a collection of more than 80 galaxies bound together by gravity. Our galaxy and Andromeda are the two dominant members, and together they influence all the smaller galaxies within a region about 10 million light-years across. In a sense, this entire region is our galaxy's extended neighborhood, where the combined gravity of the Milky Way and Andromeda determines the fate of dozens of smaller galaxies. Within the local group, our galaxy's influence is constantly at work. We're currently absorbing several smaller galaxies, including the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy. These galactic mergers add their stars to our own, gradually increasing the Milky Way's size and mass. It's a process that has been going on for billions of years and will continue for billions more. The discovery of ultra-faint dwarf galaxies has pushed the boundaries of what we consider part of our galactic system. These tiny galaxies, some containing only a few thousand stars, orbit the Milky Way at distances of up to 1 million light-years. They're so faint that we've only discovered them in the past 2 decades, thanks to sensitive digital sky surveys. Each new discovery extends our understanding of how far our galaxy's influence truly reaches. The interaction between our galaxy and its satellites reveals another layer of the Milky Way's extended reach: tidal streams. When a smaller galaxy ventures too close, our galaxy's gravity pulls more strongly on the near side than the far side, stretching the victim like cosmic taffy. These tidal forces can completely disrupt satellite galaxies, spreading their stars along vast arcs that trace their orbital paths. We've now identified over 20 such streams, some extending hundreds of thousands of light-years, creating a complex web of stellar debris around our galaxy. One of the most spectacular examples is the Orphan Stream, discovered in 2006. This stream of stars has no obvious parent galaxy. Its progenitor was completely destroyed by tidal forces, leaving only this stellar river as evidence of its existence. The stream extends over 200,000 light-years, arcing high above the galactic disk. It's like finding a ghost's footprints, showing where a galaxy once traveled before our Milky Way tore it apart. The concept of our galaxy's sphere of influence becomes even more fascinating when we consider the cosmic web, the largest structure in the universe. Galaxies aren't randomly scattered through space. They're connected by filaments of dark matter and gas, forming a vast network that spans the observable universe. The Milky Way sits at the intersection of several of these cosmic filaments, which channel matter toward our galaxy from distances of tens of millions of light-years. Recent simulations using supercomputers have shown that our galaxy's formation and growth can't be understood in isolation. Matter flowing along these cosmic filaments has been feeding our galaxy for billions of years, and this inflow zone extends far beyond what we traditionally consider the galaxy's edge. In a sense, our galaxy's reach extends along these cosmic highways, connecting us to the large-scale structure of the universe itself. The discovery of the Radcliffe wave in 2020 added another dimension to our understanding of the galaxy's extent. This massive, wave-like structure of stellar nurseries stretches 9,000 light-years and undulates above and below the galactic plane. It's the largest coherent structure ever found in our galactic neighborhood, and we're actually inside it. The Sun passed through this wave about 13 million years ago and will encounter it again in another 13 million years. It shows that even within what we thought was well-mapped territory, our galaxy holds surprises about its true structure and extent. Let's talk about something truly mind-bending: our galaxy's future reach. The Milky Way and Andromeda Galaxy are on a collision course, approaching each other at about 110 kilometers per second. In approximately 4 billion years, these two galactic giants will merge, creating a new elliptical galaxy that astronomers have already nicknamed Milkdromeda. When this happens, the reach of our galaxy will expand dramatically, encompassing all of Andromeda's stars, gas, and dark matter. But the merger process will begin long before the galaxies actually collide. As they approach each other, their gravitational fields will start to interact at distances of millions of light-years. Tidal forces will distort both galaxies, pulling out long streams of stars and gas. Computer simulations show that some stars will be flung out into intergalactic space, traveling millions of light-years from their parent galaxies. In a sense, the collision will extend both galaxies' reach far beyond their current boundaries. The role of supermassive black holes in defining our galaxy's reach is another fascinating aspect. At the center of the Milky Way lurks Sagittarius A, a black hole with a mass 4 million times that of our Sun. While this might seem small compared to the galaxy's total mass of about 1 trillion solar masses, its influence extends throughout the galaxy. The black hole's gravity affects the orbits of stars thousands of light-years away, and its past activity, as evidenced by the Fermi bubbles, has shaped the galaxy on even larger scales. Recent observations using the Event Horizon Telescope and other instruments have shown that Sagittarius A is relatively quiet now, but it hasn't always been so. Evidence suggests that our galaxy's central black hole has experienced periods of intense activity, swallowing large amounts of gas and blasting out powerful jets. These jets can extend hundreds of thousands of light-years, carrying energy and matter far beyond the galaxy's stellar disk. They're like cosmic geysers, showing that our galaxy's influence can be projected across vast distances. The discovery of hypervelocity stars adds another dimension to our galaxy's reach. These stellar speedsters are traveling so fast, over 1,000 kilometers per second, that they can escape the galaxy's gravitational pull entirely. Most were probably ejected from the galactic center after close encounters with the supermassive black hole. As they race away from the galaxy, they carry with them the chemical elements forged in our galaxy's stars, spreading the Milky Way's influence into intergalactic space. Some of these hypervelocity stars will travel millions of light-years from our galaxy, becoming lonely wanderers in the vast emptiness between galaxies. Yet they remain forever marked by their origin, carrying the chemical fingerprint of the Milky Way in their composition. In a poetic sense, these stellar exiles extend our galaxy's reach across cosmic voids like messages in bottles cast into an infinite ocean. The magnetic field of our galaxy presents another fascinating aspect of its extended influence. Using radio telescopes and observations of polarized light from distant stars, astronomers have mapped the Milky Way's magnetic field extending far beyond the visible disk. These magnetic field lines stretch above and below the galactic plane, creating a magnetosphere that influences charged particles across hundreds of thousands of light-years. Cosmic rays, high-energy particles from supernovae and other violent events spiral along these field lines, trapped in our galaxy's magnetic embrace. Recent discoveries have shown that our galaxy's magnetic field isn't uniform, but has a complex structure with reversals and twists. The field is strongest in the spiral arms and weaker in the interarm regions. Above and below the disk, the field forms enormous loops and bubbles, shaped by stellar winds and supernova explosions. This magnetic architecture affects everything from star formation to the propagation of radio waves, showing that our galaxy's influence extends through multiple physical mechanisms. The concept of the galactic habitable zone adds another layer to understanding our galaxy's reach. Just as solar systems have habitable zones where liquid water can exist on planetary surfaces, our galaxy has regions where conditions are suitable for life as we know it. Too close to the galactic center and the radiation from densely packed stars and frequent supernovae would sterilize any planets. Too far out, and there aren't enough heavy elements to form rocky planets, or the complex chemistry necessary for life. We find ourselves in the galactic sweet spot, about 26,000 light-years from the center, where conditions have remained relatively stable for billions of years. But this habitable zone isn't static. It migrates outward as the galaxy evolves and stellar populations age. Understanding how far this zone extends and how it changes over time helps us grasp another dimension of our galaxy's reach, its potential to harbor life throughout its vast expanse. The discovery of exoplanets has revolutionized our understanding of planetary systems throughout the galaxy. The Kepler Space Telescope and other missions have shown that planets are common, with most stars hosting at least one planet. If we extrapolate these findings across the entire galaxy, there could be hundreds of billions of planets within the Milky Way's sphere of influence. Each of these worlds is held in our galaxy's gravitational embrace, making them part of our extended cosmic family. But our galaxy's reach extends beyond just physical influence. It also encompasses time. Light from the most distant parts of our galaxy takes tens of thousands of years to reach us. When we observe the far edges of the galactic halo, we're seeing them as they were when humans were still in the Stone Age. This temporal dimension means our galaxy's reach extends not just through space but through time, connecting us to our cosmic past. The interaction between our galaxy and the intergalactic medium reveals yet another aspect of its reach. Our galaxy isn't sitting in a perfect vacuum. It's surrounded by a thin, intergalactic medium of gas and dark matter. As our galaxy moves through space at about 600 kilometers per second, relative to the cosmic microwave background, it creates a bow shock in this medium, like a boat moving through water. This interaction zone extends millions of light-years ahead of our galaxy in its direction of motion. Recent studies using quasar absorption lines have revealed that our galaxy is stripping gas from the intergalactic medium as it moves. This cosmic vacuum cleaner effect pulls in fresh hydrogen gas from distances of over 1 million light-years, providing raw material for future star formation. It's estimated that our galaxy accretes about 1 solar mass of gas per year through this process, showing that the Milky Way is still growing and extending its reach. The role of satellite galaxies in defining our galaxy's extent is more complex than simple orbital mechanics. These smaller galaxies don't just passively orbit, they actively interact with the Milky Way and with each other. The large and small Magellanic Clouds, for example, are interacting not just with our galaxy, but with each other, creating the Magellanic Bridge, a stream of gas connecting the two galaxies. This three-way gravitational dance extends our galaxy's sphere of influence in complex, dynamic patterns. Recent simulations have shown that satellite galaxies can significantly disturb the dark matter halo of their host galaxy. As they orbit, they create wakes and density waves in the dark matter, like boats creating ripples in a pond. These disturbances can extend for hundreds of thousands of light-years, showing that our galaxy's dark matter halo is not a static, smooth distribution, but a dynamic, churning sea of invisible matter. The discovery of the vast polar structure, also known as the VPOS, has challenged our understanding of how far our galaxy's organized influence extends. This is a rotating plane of satellite galaxies, globular clusters, and stellar streams that orbits the Milky Way in a coordinated fashion. The structure extends over 1 million light-years and includes about half, of our galaxy's known satellite galaxies. It's as if these smaller galaxies aren't randomly distributed but are organized into a vast, rotating disk around our galaxy. This discovery has profound implications for our understanding of galaxy formation and dark matter. Standard models predict that satellite galaxies should be randomly distributed around their host, but the VPOS shows clear organization. Some astronomers suggest this structure formed when the Milky Way tidally disrupted a larger galaxy billions of years ago, with the debris forming this organized plane. If true, it means our galaxy's formative influence can create ordered structures extending over 1 million light-years. Let's explore the concept of our galaxy's gravitational wake. As the Milky Way moves through the universe, it doesn't travel alone. It drags along its entire retinue of satellite galaxies, stellar streams, and dark matter halo. This creates a gravitational wake extending millions of light-years behind our galaxy's direction of motion. Recent studies suggest that the large Magellanic Cloud, our most massive satellite galaxy, is creating its own wake within our galaxy's wake, like a boat being towed behind a larger ship. The discovery of ultra-diffuse galaxies in our cosmic neighborhood has expanded our understanding of what constitutes our galaxy's extended family. These ghostly galaxies are as large as the Milky Way but contain only about 1% as many stars. Some of these ultra-diffuse galaxies orbit within our local group, influenced by our galaxy's gravity, despite being millions of light-years away. They're like cosmic phantoms, barely visible but still bound to our galaxy's gravitational web. One of the most exciting recent developments is the detection of our galaxy's splash zone, regions where infalling satellite galaxies have deposited their stars into our galaxy's halo. The Gaia Space Telescope has identified several of these splash zones, including the famous Gaia Sausage, the remnant of a massive galaxy that collided with the Milky Way about 8 to 10 billion years ago. This ancient collision deposited stars throughout our galaxy's halo, extending our galaxy's stellar population to distances we're still discovering. The chemical influence of our galaxy extends even farther than its gravitational reach. Supernova explosions in our galaxy can launch heavy elements at tremendous speeds, sending them into intergalactic space. These chemical ambassadors carry the products of stellar nucleosynthesis, elements like carbon, oxygen, and iron, far beyond our galaxy's borders. Over billions of years, our galaxy has been seeding the intergalactic medium with the elements necessary for planets and potentially life. Recent observations have detected metal-enriched gas clouds hundreds of thousands of light-years from any galaxy. Some of this enriched gas likely came from our own Milky Way, expelled by ancient supernovae or galactic winds. In this way, our galaxy's chemical influence extends into the void between galaxies, contributing to the slow enrichment of the universe with heavy elements. The phenomenon of Ram pressure stripping reveals another aspect of our galaxy's extended influence. As satellite galaxies move through our galaxy's hot gas halo, the pressure strips away their own gas, leaving trails that can extend for hundreds of thousands of light-years. The Magellanic Stream is the most spectacular example, but smaller streams from other satellites crisscross our galaxy's halo. These stripped gas trails become part of our galaxy's extended atmosphere, eventually falling back to fuel future star formation. Dark energy, the mysterious force causing the universe's expansion to accelerate, sets an ultimate limit on our galaxy's future reach. As the universe expands, galaxies beyond our local group are receding from us at ever-increasing speeds. Eventually, they'll pass beyond our cosmic horizon, becoming forever unreachable. In about 100 billion years, our galaxy's observable universe will shrink to just our local group, with all other galaxies having receded beyond the point where their light can reach us. This cosmic isolation means that our galaxy's maximum sphere of influence is ultimately bounded by dark energy. While our gravitational reach theoretically extends forever, the accelerating expansion of space means there's a practical limit to how far our galaxy can ever influence or be influenced by distant structures. We live in a brief cosmic moment when we can still see and study other galaxy groups and clusters. The discovery of dark matter subhalos within our galaxy's main halo has revealed yet another layer of structure. These invisible clumps of dark matter, ranging from the mass of Earth to the mass of a dwarf galaxy, orbit within our galaxy's dark matter halo. There could be thousands or even millions of these dark matter clumps extending throughout the million light-year span of our galaxy's dark matter distribution. They're like invisible satellites, detectable only through their gravitational effects on visible matter. These dark matter subhalos occasionally pass through the disk of our galaxy, potentially triggering bursts of star formation or disrupting the orbits of stars. Some scientists suggest that one of these invisible clumps might have passed through our solar system's outer regions millions of years ago, disturbing the Oort cloud and sending comets toward the inner solar system. If true, our galaxy's dark matter structure could have directly influenced the evolution of life on Earth through comet impacts. The relationship between our galaxy and cosmic voids, vast regions of space containing very few galaxies, reveals another aspect of its reach. The Milky Way sits near the edge of the local void, an enormous region roughly 200 million light-years across that contains far fewer galaxies than average. Our galaxy's position relative to this void affects its motion through space and the rate at which it accretes matter from the intergalactic medium. In a sense, even the absence of matter defines our galaxy's cosmic context and extent. Recent studies of the cosmic microwave background radiation have revealed that our entire local group, including the Milky Way, is moving through space at about 600 kilometers per second toward a mysterious gravitational anomaly called the Great Attractor. This motion, caused by the gravitational pull of massive galaxy clusters hundreds of millions of light-years away, shows that our galaxy is influenced by and connected to structures far beyond its immediate neighborhood. The concept of our galaxy's fossil record extends its reach through time in fascinating ways. The oldest stars in our galaxy's halo formed over 13 billion years ago, just a few 100 million years after the Big Bang. These ancient stars carry information about the conditions in the early universe, including the properties of the first galaxies that merged to form the Milky Way. By studying these stellar fossils, we can trace our galaxy's reach back to the cosmic dawn. The discovery of stellar populations with different chemical compositions has revealed that our galaxy is like an archaeological site, with layers of history preserved in the motions and compositions of its stars. The thick disk contains stars from our galaxy's turbulent youth, while the thin disk where our Sun resides represents more recent, orderly star formation. Each population extends to different distances and tells a different chapter of our galaxy's story. Let's consider the extraordinary concept of galactic wind. Our galaxy generates a wind of hot gas, flowing outward from regions of intense star formation. This galactic wind, driven by the combined effect of thousands of supernovae and stellar winds, can reach speeds of hundreds of kilometers per second. The wind carries gas, dust, and heavy elements far above and below the galactic disk, creating a cycle of material that extends hundreds of thousands of light-years from the galaxy. Recent X-ray observations have shown that this galactic wind isn't uniform but has a complex, multi-phase structure. Hot gas at millions of degrees coexists with cooler clouds, creating a cosmic weather system of unimaginable scale. Some of this expelled gas will eventually cool and fall back onto the galaxy, while some will escape forever into intergalactic space. This breathing process has been going on for billions of years, constantly extending and refreshing our galaxy's atmosphere. The role of cosmic rays in defining our galaxy's reach adds another dimension to this story. These high-energy particles, accelerated by supernovae and other violent events, fill our galaxy and extend far beyond it. The Milky Way acts like a giant particle accelerator, shooting cosmic rays into intergalactic space. Some of these particles have energy so high that they can travel millions of light-years before being deflected by intergalactic magnetic fields. The Voyager spacecraft, launched in 1977, have recently crossed the heliopause, the boundary where our Sun's influence gives way to the interstellar medium. Their measurements show that even in interstellar space, they're still detecting cosmic rays accelerated by our galaxy. These particles create a cosmic ray halo around our galaxy that extends far beyond the stars, another invisible component of our galaxy's extended reach. The phenomenon of galactic archaeology has revealed that our galaxy's influence extends through ghost galaxies, the completely disrupted remains of ancient satellites. The Helmi stream, the Sequoia galaxy, and other ancient structures are now completely dissolved, their stars scattered throughout our galaxy's halo. Yet by tracking the motions and compositions of these stars, astronomers can reconstruct galaxies that died billions of years ago. Our galaxy is thus a cosmic graveyard, containing the remains of dozens or possibly hundreds of smaller galaxies. The discovery of the Radcliffe wave mentioned earlier has implications beyond just its size. This wave-like structure suggests that our galaxy's disk isn't as simple as we thought. There might be other large-scale waves or corrugations that we haven't detected yet, potentially extending the galaxy's structured disk much farther than current estimates. It's as if we've been looking at our galaxy as a flat photograph, when it's actually a three-dimensional sculpture with complex undulations. The interaction between our galaxy and the cosmic web of dark matter filaments reveals perhaps the most extensive reach of all. These filaments, which connect galaxy clusters across hundreds of millions of light-years, act as cosmic highways channeling matter toward galaxies. The Milky Way sits at the intersection of several such filaments, and computer simulations suggest that matter can flow along these structures from distances of 50 million light-years or more, eventually becoming part of our galaxy. Recent observations using the Subaru telescope have actually detected some of these cosmic filaments through weak gravitational lensing, the subtle distortion of background galaxy images by the filament's gravity. These observations show that our galaxy isn't an island, but a node in a vast cosmic network, with tendrils of influence extending along these dark matter bridges to neighboring galaxy groups and beyond. The discovery of ultra-high energy cosmic rays has added another puzzle to our galaxy's extent. Some cosmic rays detected on Earth have energies so high that they couldn't have traveled more than about 50 million light-years without losing energy to interactions with the cosmic microwave background. Yet their sources remain mysterious. Some might come from our galaxy's extended halo, or from the interaction zones where our galaxy's influence meets that of our neighbors. Let's explore the fascinating concept of our galaxy's feeding zones. Observations have shown that galaxies don't grow in isolation, but are constantly fed by streams of cold gas flowing in from the intergalactic medium. For the Milky Way, these feeding zones extend millions of light-years, funneling gas along dark matter filaments toward our galaxy. This cosmic supply chain has been operating for billions of years, providing the raw material for continued star formation. The role of galaxy groups in defining our galaxy's reach introduces another level of complexity. The Milky Way isn't just influenced by individual neighbor galaxies, but by the collective gravity of the entire local group. This group gravity creates a shared sphere of influence extending about 5 million light-years from the group's center of mass. Within this region, the combined gravity of all local group galaxies dominates over the expansion of the universe. Recent discoveries about satellite galaxy planes around other galaxies have shown that organized structures like our VPOS might be common. The Andromeda Galaxy has its own plane of satellites, and similar structures have been found around other large galaxies. This suggests that our galaxy's ability to organize matter into planar structures might extend even farther than we currently observe, possibly encompassing undiscovered ultra-faint satellites. The phenomenon of galactic cannibalism reveals our galaxy's ongoing extension of its reach. Right now, the Milky Way is actively consuming several smaller galaxies. The Sagittarius dwarf spheroidal galaxy is being stretched into a stream that wraps around our galaxy multiple times. The Canis major dwarf galaxy is being absorbed into our disk. Each merger adds not just stars, but extends our galaxy's reach to encompass the victim's former territories. The discovery of young stars in unexpected places has challenged our understanding of where our galaxy ends. Some young blue stars have been found hundreds of thousands of light-years from the galactic center, in regions where star formation shouldn't be occurring. These stars might have formed in place from gas compressed by galactic interactions, or they might have been ejected from the disk while still forming. Either way, they extend the region of active star formation far beyond traditional boundaries. The concept of our galaxy's gravitational focus points, called Lagrange points, creates regions of stability far from the galactic center. Just as the Earth-Sun system has points where gravitational forces balance, our galaxy has similar points relative to its satellites and neighbors. Objects at these points can remain stable for billions of years, effectively extending our galaxy's organized structure to distances of over 1 million light-years. Dark energy's effect on our galaxy's future reach presents a sobering long-term perspective. As the universe's expansion accelerates, the local group will become increasingly isolated. In about 100 billion years, all galaxies beyond our local group will have receded beyond our cosmic horizon. At that point, our galaxy's reach will be absolutely bounded, unable to influence or be influenced by anything beyond the local group. The discovery of tidal dwarf galaxies, small galaxies formed from material pulled out during galaxy interactions, shows that our galaxy can actually create new galaxies at its periphery. When the Milky Way and Andromeda eventually collide, the tidal forces will likely create several new dwarf galaxies from the stripped gas and stars. These newborn galaxies will orbit the merged galaxy, extending its family of satellites even farther into space. The role of supermassive black hole jets in defining galactic reach is another frontier of research. While our galaxy's central black hole is currently quiet, evidence suggests it has been active in the past. When active, supermassive black holes can launch jets extending hundreds of thousands or even millions of light-years. If our galaxy's black hole becomes active again, perhaps during the merger with Andromeda, these jets could extend our galaxy's energetic influence far into intergalactic space. The fascinating phenomenon of galactic fountains reveals another dimension of our galaxy's reach. When massive stars explode as supernovae in the disk, they blast hot gas high above the galactic plane. This gas can rise hundreds of thousands of light-years before cooling and falling back down, creating a cosmic fountain. The Hubble Space Telescope has observed these fountains in action, detecting clouds of gas suspended far above the disk, held up temporarily by pressure from below before gravity pulls them back. These galactic fountains don't just recycle gas, they also transport heavy elements from the disk to the halo. Elements forged in the nuclear furnaces of massive stars get distributed throughout a volume much larger than the stellar disk itself. This process has been operating for billions of years, gradually enriching our galaxy's entire sphere of influence with the elements necessary for rocky planets and life. Recent studies of globular clusters have revealed that these ancient stellar cities extend our galaxy's organized structure to surprising distances. Some globular clusters orbit at distances of 400,000 light-years from the galactic center, yet they remain gravitationally bound to our galaxy. These clusters, containing hundreds of thousands or even millions of stars packed into spheres just a few hundred light-years across, are like distant outposts marking the extent of our galaxy's domain. The discovery of stellar shells around our galaxy has added another layer to understanding its reach. These shells are formed when a small galaxy is disrupted by tidal forces, leaving its stars in shell-like structures at specific distances from the galactic center. Recent surveys have identified several such shells, some extending to 300,000 light-years. They're like growth rings in a tree, each one marking an ancient galactic merger that extended our galaxy's reach. Let's explore the mind-bending concept of our galaxy's causal horizon. Due to the finite speed of light and the age of the universe, there's a maximum distance from which our galaxy could have received any influence since the Big Bang. This cosmic horizon, currently about 46 billion light-years away due to the expansion of space, represents the absolute limit of our galaxy's potential connections. Everything beyond this horizon exists in a realm that has never and can never influence our galaxy. The relationship between our galaxy and the cosmic microwave background radiation reveals another aspect of its reach. As our galaxy moves through space, it creates a dipole pattern in the CMB, slightly hotter in the direction of motion and slightly cooler behind. This effect, called the kinematic dipole, extends our galaxy's influence to the very edge of the observable universe as our motion affects how we observe the most distant light in the cosmos. Recent discoveries about the local sheet, a flattened region of galaxies including the Milky Way, show that our galaxy's environment extends beyond just the local group. This sheet, about 30 million light-years across and only a few million light-years thick, contains several galaxy groups that move together through space. Our galaxy's motion and evolution are influenced by this larger structure, showing that its cosmic context extends far beyond its immediate neighbors. The phenomenon of induced star formation reveals how our galaxy's influence can trigger activity in its satellites. When satellite galaxies pass through our galaxy's gas halo or experience tidal forces, the compression can trigger bursts of star formation. The Large Magellanic Cloud is currently experiencing such a burst, likely triggered by its interaction with our galaxy. In this way, the Milky Way acts as a cosmic catalyst, sparking stellar birth in galaxies hundreds of thousands of light-years away. The discovery of hypercompact stellar systems, dense clusters of stars ejected from our galaxy at high speeds, shows that our galaxy can launch entire stellar communities into intergalactic space. These systems, containing thousands of stars bound together, travel as units far from our galaxy. They're like seeds cast into the cosmic wind, carrying pieces of our galaxy's stellar population to distances we're still discovering. The role of magnetic fields in defining our galaxy's reach extends beyond the local field. Our galaxy's magnetic field interacts with the intergalactic magnetic field, creating a magnetic interface that can extend millions of light-years from the galaxy. This magnetic boundary affects how cosmic rays enter our galaxy and how our galaxy's own cosmic rays escape into intergalactic space. It's an invisible barrier that partially shields our galaxy, while also connecting it to the magnetic web of the universe. Recent simulations of galaxy formation have shown that our galaxy's influence began even before it fully formed. The dark matter halo that would become our galaxy began attracting matter when the universe was less than 1 billion years old. This primordial sphere of influence, extending millions of light-years, determined which gas clouds and smaller halos would eventually merge to form the Milky Way we see today. The discovery of the South Pole Wall, a massive cosmic structure stretching 1.4 billion light-years, has raised questions about how such large structures influence galaxies like ours. While the wall is hundreds of millions of light-years away, its gravitational pull contributes to our galaxy's motion through space. These cosmic walls and voids create a gravitational landscape that affects galaxies across billions of light-years. The concept of our galaxy's memory adds a temporal dimension to its reach. Every star in our galaxy carries information about the conditions when it formed. Its chemical composition, its orbit, its age, all tell parts of our galaxy's history. The Gaia mission has revealed that our galaxy remembers ancient events through the motions of its stars. Collisions that happened billions of years ago left signatures in stellar velocities that we can still detect today. In this sense, our galaxy's reach extends through time, preserving records of interactions with galaxies that no longer exist. One of the most remarkable recent discoveries is the existence of galactic shells of dark matter. Computer simulations suggest that when our galaxy absorbed smaller galaxies, their dark matter didn't mix smoothly, but formed shell-like structures in our halo. These invisible shells, potentially extending to 500,000 light-years, affect how stars and gas clouds move through our galaxy's outskirts. We're essentially surrounded by invisible archaeological layers from ancient galactic mergers. The phenomenon of splashback radius provides another way to define our galaxy's boundary. This is the distance where matter falling toward our galaxy for the first time reaches its closest approach before swinging back out. For the Milky Way, this splashback radius is estimated to be about 1 million light-years. It marks a physical boundary between material that's truly part of our galaxy system and material that's still falling in for the first time. Recent observations of quasars, extremely bright galactic cores powered by supermassive black holes, have been used to probe our galaxy's extended gas halo. When quasar light passes through our galaxy's halo, specific wavelengths are absorbed, revealing the presence and properties of gas hundreds of thousands of light-years from the galactic center. These observations show that our galaxy's gaseous atmosphere is not smooth but has a complex, clumpy structure extending farther than previously thought. The discovery of runaway stars fleeing our galaxy at incredible speeds reveals another way our galaxy extends its influence. Some of these stars, ejected by gravitational encounters with our central black hole or by supernova explosions in binary systems, are traveling fast enough to escape our galaxy entirely. They'll carry matter forged in our galaxy millions of light-years into intergalactic space, becoming lonely ambassadors of the Milky Way in the cosmic void. Let's explore the fascinating concept of our galaxy's bow shock. As the Milky Way plows through the intergalactic medium at hundreds of kilometers per second, it creates a shock wave in front of it, similar to the bow wave of a ship. This shock heats and compresses the intergalactic gas, creating a zone of turbulence that extends millions of light-years ahead of our galaxy. Any gas entering our galaxy must first pass through this cosmic shock front. The relationship between our galaxy and ultra-high energy neutrinos adds another layer to its extended influence. These ghostly particles, produced in the most violent cosmic events, stream through our galaxy, barely interacting with matter. Yet some are produced within our galaxy's sphere of influence, possibly in the jets from our central black hole or in cosmic ray interactions. These neutrinos carry information about our galaxy to the farthest reaches of the universe, passing through matter as if it weren't there. Recent studies of the Milky Way's rotation curve, how fast stars orbit at different distances from the center, have revealed that our galaxy's dark matter halo might not be spherical but triaxial, shaped like a cosmic football. This asymmetric shape means our galaxy's gravitational influence varies with direction, extending farther along some axes than others. It's as if our galaxy reaches out with invisible arms of dark matter in preferred directions. The discovery of the dipole repeller, a mysterious void that appears to be pushing our local group through space, shows that our galaxy's motion is influenced by the absence of matter as well as its presence. This cosmic void, centered about 600 million light-years away, has so little matter that its lack of gravitational pull effectively pushes us toward denser regions. Our galaxy's trajectory through space is thus shaped by structures and non-structures across hundreds of millions of light-years. The phenomenon of ram pressure stripping on our own galaxy reveals that we're not immune to environmental effects. As we move through the local group medium, the pressure strips some gas from our galaxy's outer regions. This process is subtle but continuous, meaning our galaxy is slowly losing some of its most extended gas to the intergalactic medium. At the same time, we're stripping gas from our satellites, creating a complex exchange of matter within our sphere of influence. The concept of gravitational lensing by our galaxy shows its influence on our perception of the entire universe. Our galaxy's mass bends light from more distant objects, acting as a weak gravitational lens. This means every observation we make of distant galaxies is slightly distorted by our own galaxy's gravity. In a sense, our galaxy's gravitational reach extends to the edge of the observable universe, affecting every photon that passes near it. The recent detection of the cosmic web in emission, rather than just absorption, has revealed that the gas filaments connecting galaxies actually glow faintly in ultraviolet light. Using the MUSE instrument on the Very Large Telescope, astronomers have directly observed these glowing filaments extending from our galaxy toward our cosmic neighbors. It's as if we've discovered that our galaxy is connected to the universe by glowing threads of gas, visible proof of the cosmic web that binds all galaxies together. One of the most philosophically profound aspects of our galaxy's reach is its role in the anthropic principle. The specific extent of our galaxy, not too large, not too small, might be crucial for the existence of life. A smaller galaxy might not have enough heavy elements or stable orbits for planetary systems. A larger galaxy might have too much radiation from active star formation or too many gravitational disruptions. Our galaxy's particular reach, extending just far enough to gather resources while maintaining stability, might be one of the many cosmic coincidences that make our existence possible. The discovery of time delays in gravitational lensing has shown that our galaxy can affect how we perceive time itself in distant objects. When our galaxy's gravity bends light from a distant supernova or quasar, different light paths have different lengths, causing us to see the same event multiple times at different moments. Our galaxy thus acts as a cosmic time machine, allowing us to observe the same cosmic events from multiple perspectives separated by months or years. Recent studies of dwarf galaxies at the edge of our galaxy's influence have revealed that they're not just orbiting randomly, but show signs of coherent rotation. This suggests our galaxy's organizational influence extends even to its most distant satellites. It's as if our galaxy conducts a cosmic orchestra with even the faintest, most distant members following the gravitational symphony. The phenomenon of galactic feedback reveals how our galaxy's influence is self-regulating. When star formation becomes too intense, the energy from supernovae and stellar winds heats the gas, preventing further star formation. When star formation slows, gas cools and collapses, triggering new stellar births. This feedback cycle operates throughout our galaxy's sphere of influence, creating a self-regulating system that has maintained stability for billions of years. Let's consider the extraordinary fact that our galaxy's reach extends into the quantum realm. The matter in our galaxy's outer reaches is so diffuse that quantum effects become important. Individual atoms can be separated by meters or more, yet they're still bound by our galaxy's gravity. In these extreme conditions, our galaxy becomes a laboratory for quantum mechanics on macroscopic scales. The discovery of our galaxy's connection to the cosmic dawn, the era when the first stars formed, extends its reach back to the very beginning of cosmic history. Some of the stars in our galaxy's halo formed when the universe was just 200 million years old. These ancient stars have been part of our galaxy's story for over 13 billion years, connecting us directly to the universe's infancy. Recent observations have shown that our galaxy's influence extends to the cosmic ray spectrum across the entire electromagnetic range. From radio waves to gamma rays, our galaxy shapes the radiation environment for millions of light years around us. This creates a unique electromagnetic ecosystem that affects everything from planet formation to the potential for life. The concept of our galaxy as a cosmic engine becomes clear when we consider its total energy output. Our galaxy converts matter into energy through nuclear fusion in stars, gravitational accretion onto black holes, and cosmic ray acceleration. This energy, totaling about 10 to the 44 watts, radiates into space, extending our galaxy's energetic influence across the universe. Every second, our galaxy pumps enough energy into space to power billions of civilizations. As we look to the future, the merger with Andromeda will dramatically extend our galaxy's reach. The combined galaxy will have a sphere of influence extending over 2 million light-years, encompassing dozens of smaller galaxies. This future mega-galaxy will be one of the dominant structures in the local group, its gravitational reach extending to the very boundaries of what will then be our observable universe. The profound realization is that we're not just living in a galaxy, we're part of a vast, interconnected system that extends far beyond what we can see with our eyes. Every atom in your body was forged in this extended galactic system. The calcium in your bones might have come from a supernova in a satellite galaxy hundreds of thousands of light years away. The water in your cells might contain hydrogen that has circulated through our galaxy's fountain system multiple times over billions of years. Our galaxy's reach ultimately connects us to the entire universe. Through gravitational waves, we're connected to every mass in the observable universe. Through electromagnetic radiation, we exchange photons with galaxies billions of light years away. Through the cosmic web, we're part of the universe's largest structures. We're not isolated on a small planet in one galaxy. We're part of a cosmic network that spans space and time. As you look up at the night sky, remember that you're seeing just the tiniest fraction of our galaxy's true extent. Beyond those visible stars lies an empire of dark matter, magnetic fields, hot gas, and gravitational influence stretching millions of light years in every direction. You're not just in the Milky Way, you're part of a vast cosmic structure that connects you to the universe itself. Our galaxy's reach in all its magnificent complexity reminds us that we're part of something far grander than we ever imagined, citizens of a cosmic nation whose boundaries stretch to the very limits of physical influence in our corner of the universe. If you made it this far, make sure to subscribe to the channel and give a thumbs up. And I am sure you will love this other video at the left side of the screen. How big is the universe? If you're fascinated by astronomy, space, and the biggest mysteries in science, this is the ultimate guide to the size of the universe and your place within it. See you there.